Hello everyone, welcome to lecture 9. In this lecture, I will talk about machine learning and the k-nearest neighbors algorithm. And I will show some example in some application in machine learning. So let's talk about the machine learning in this lecture. And machine learning is a huge field and in computer science, and currently almost all application are based on the machine learning and try to learn machine and try to train a machine to do some task in the computer science. So in this lecture, I will talk about machine learning and try to cover a broad overview of that, and maybe a handful algorithms and machine learning, just a simple algorithm to show how it's work, and maybe that can be useful in your research. So there are some application in the machine learning, and the most common application in this area is computer vision. And then computer vision, we have mostly we have three tasks that for example, for the first one is the classification, and in the classification, the input is an image, and the machine should predict a label for this image. So, for example, here we have an image of the cat, and the label is the cat, and the machine, after seeing this image, should say that okay, this image is a cat or dog. So this is a first task in computer vision. The second one is the detection, and in detection task, we also have an image, but we want to detect an object in that image instead of just predicting a label for that. For example, here we want to detect a box for the dog, and then we want to take that the computer can see a cat in this image, and for each object that we can see in the image, we want to predict a box to detect the exact position of the object in the image. And the third one is the segmentation, which is so similar to the second task, detection. But in the segmentation, as you can see, we want to find the exactly area of the object in the image, not just the box or something like this. So this is the first common application in machine learning, and the second one is a natural language processing. So this is a broad task in computer science, but I just want to mention a simple example here for the natural language processing. So, for example, we have a product, and we get a lot of reviews from the user, and we want to actually have a machine, have a system that get these reviews and say predict that the reviews is a positive or negative. So, for example, we have two reviews here, and then one of them is positive and one of them is negative. So, by natural language processing, we can find that, and sentiment analysis, we can find that okay, this review is positive about the product, and this review is negative. So, by doing this, if you have a product that you are getting reviews from the user, you can find that most of the user are satisfied with the product or not. And the third one is the information retrieval. And in information retrieval, you get a query from the user, and you want to retrieve some documents for the user. to in a rank list and show to the user. So a simple task that we can solve in the information retrieval by machine learning is that, for example, here we enter a query to the search engine, and the search engine recommends some terms to autocomplete your query based on some features that we feed to the machine in the training. So, and the system needs to predict some terms and then show these terms as the next words that you want to enter to the search engine to complete your query. And the computer vision, natural language processing, information retrieval are area in the computer science, but machine learning can be applied in other area from other fields, for example, bioinformatics. And I'm not familiar with that, but I'm sure that they are using machine learning, for example, for example, if you get a sequence of the protein and you want to predict something about the next things in the protein, you need to use machine learning. You can use machine learning for that. And I just want to mention that machine learning is a broad area that can be applied in any field, not even and not only the computer science, but also the other fields. And let's have a definition for the machine learning. Machine learning is a collection of the algorithm that can detect and exploit patterns in the data. So we have lots of algorithm to do that, and we are getting more advanced algorithms every day for the machine learning. So for the goal of the machine learning, we can have four options, and as a first goal that we can have in the machine learning is that we want to predict some labels out or outcome given some data points. This means that we are getting some features from training data and we want to predict the labels or the outcome. And this example, for example, classification, we are predicting a label for this image. So most of this application and task that I mentioned are from the first category that we want to accurately predict a label for the data. And the second one is the generate data point that a human cannot find the difference between the generated data and the real data. So this also is another goal for the machine learning, to generate data based on some real data. And we also have some algorithm in the machine learning to explain patterns in the data, and by using model parameters. And this also can be the goal of for some algorithms in the machine learning. So we just need to find some patterns in the data. For example, clustering, I think, can be a good example of this category. So, and also as a last goal, we consider that we have an agent, and the agent can act in an environment. So um, the agent needs to achieve a goal in the environment. So if we want to control the agent, we need to train the agent based on some machine learning algorithm. And this also can be a good example of the reinforcement learning. So for example, in a game playing, uh, the agent needs to win the game, which is the goal of the task. And to win in the game, we need to do some action in the environment. So this also can be a goal of the uh, machine learning application and algorithm. And we have some paradigms for the machine learning. The first one is the classification that I briefly explained that in the previous slide. And in the classification, we want to get some features as an input and then map this input to the label. So, for example, here the input is a simple image of the cat, and then the output label is the cat or dog or something like this. So the machine learning needs to map these features to accurate the labels. And another one is the regression that map inputs to real value. So for the classification, the labels are discrete value. For example, dog, cat, or something like this. But in the regression, we get the same input, but the output is the real values. For example, I have a figure here, which is the price of a stock in uh, in some days, and we get these prices and for the for the stock, and we want to predict the price of the stock in the next day. So in this case, we fit a model on the data point that we have, and based on these models, we can predict the next price in the next day. We can predict the price in the next day. And we also have another one, which is the clustering. And in the clustering, we get some data points, and then we apply some machine learning on that to group the similar input together. And as you can see, we don't have any label here. We just need to group the inputs together to as a cluster in the output, based on obviously based on the features that every points have, and we want to find the points that are similar and then group them together. And also we have reinforcement learning, which is mapping a current state to some action. So for example, in a game, we in current state, we need to do something and we need to do an action. So this means that the agent needs to get the current state and then map this current state to an action. And then by doing that action, and then finally at the end of the episode, we want to win the game. And if we win the game, we get the positive reward to the agent. If we lose the game, we get the negative reward. And another one is the generative models. And in generative model, we get some real data, and we want to generate some actually fake data that are so similar to the real data. And so for the classification, as a summary, for the classification, we need to predict the label. For the regression, we need to predict the real value. For the clustering, we need to group the similar inputs together. We don't predict anything. We just need to predict the. I mean, we don't need to predict the label or real value for each data point. We just need to group them and then say that, okay, this data point should be in the cluster 1 or something like this. In the reinforcement learning, actually we predicted actions based on some rewards, and then in generative model we are actually generating data instead of predicting something. So we have two types of machine learning algorithm. The first one is the supervised, and then the second one is unsupervised. And I want to describe the difference between these two types. In supervised learning, we have some label data. I mean, we have a data point that we have a label for that data point. For example, we have an image and we know that the label of the image is cat or duck or something like this. So, but in unsupervised approach, we need to find the structure in the unlabeled data. So in unsupervised approaches, we don't have any label for the data. We just need to find some patterns in the data. So the only difference between the supervised and unsupervised is that having a label for the data point, or we don't have. If we don't have if we don't have label for the data points, we need to do some unsupervised approach. And if we can find label for the data, supervised learning, that would be better. So let's see an example definition for the supervised learning. So in supervised learning, we as an input of the machine and system, we get the input-output pairs, which means that we get X as an input and the output is Y. So the goal is to predict the output given the X, given the input and or X. So if we already know that the input is X and we also get the output as which is Y, and the goal is to learn a probability distribution over the outputs, possible output over given this X. So for example, if we know that the output should be dog or cat, so given the image, we need to predict a probability distribution over dog and cat. So we need to predict the probability of dog given the X and probability of cat given the X. And then if the probability of dog is more than the probability of the cat, we can say that the model actually predict that this image is dog or something. So in unsupervised learning, actually we get the data point, and then we don't know anything about the labels in the unsupervised learning, and the goal of the model is learning the distribution of the data, which means that if you are getting X as an input, we need to predict the probability of X, which means that we want to know that this X is common or not, something like this. So for example, if the probability of the X is 0.9, this means that this X is a common in the data. And we also can have another category for the machine learning algorithm, which is the parametric and non-parametric. And for the parametric approaches, we can store actually the information of the model in a fixed set of parameters. And then we train a model and then apply the model to make prediction for the new inputs. So this means that we have some parameters for the approach, and the goal is to learn that parameters and then using these parameters to make a prediction for the new input. And if our algorithm is based on these parameters, we can say that the approach is parametric approach. We have another category, which is the non-parametric approach. So in non-parametric approach, we just use data to actually use the data, and then we have some assumption about the some probabilistic, and then we just need to directly make the predictions, which means that we are not learning the parameters in non-parametric approach. We just have some assumption, and then getting the data, we can make the prediction. Actually, in my mind, the non-parametric approach are less effective than a parametric approach. But if we can find an effective non-parametric approach, that would be better, because we don't need to learn any parameter for the non-parametric approach. And also, I want to mention that they can have some parameters, but these parameters are not. It's not. These parameters are not training in the training with training data. I mean, we just, for example, we have 4 or 5 parameters in non-parametric approach, and we just mentioned that, okay, if you can set these parameters to 0.1, you will get this performance. So we cannot consider these kind of parameters as a key parameters in a model, and then based on them, consider them as a parametric approach. And also, in most cases, it's so difficult to consider these kind of approaches as a model, because they are not, mostly they are not trained. They are not trained on the data, and they have some assumption based on probability or something like this. And as I mentioned, you just need to use the existing data to make some prediction, but actually we don't use the data to train the model. But let's see some example of the machine learning algorithm. For example, linear regression, logistic regression, and neural networks are parametric and supervised approaches. And for non-parametric and supervised approach, we can name the k-nearest neighbors and decision trees and RBF SVM. SVM is a support vector machines, if you already know about the machine learning algorithm. But we are not covering this in this course. But actually, in this lecture, we are going to talk about the k-nearest neighbors. And for parametric unsupervised approach, we can name k-means and mixture models. And I think we are going to cover the k-means in the next lecture. and I think you need to do a problem in the assignment 5 about the keyword. And for the non-parametric and unsupervised, we can name clustering, hierarchical clustering that we are not covering in this course. And another one is the distributed process mixture model. So if we have a system and we want to train that system or models on data uh, with with knowing the labels actually as a supervised approach, then we can use the model in the real world to predict labels. And then, for example, that you actually you get the model and train on the label data, and then after training that and you're confident about the performance of the system, you can use the system to predict some labels for the new data or real world data. So for example, here I show that we have label data and then use this label data to train the model. And then after training, we get some real world data, and then in the inference time or test time, we need to use these models to predict or for example, in the regression model, we need to predict a real value, or in a classification, we need to predict a label for the data point. So this is training and testing of your model, but what about the evaluation? And so before deploying your model in real world application, you need to know that how good or bad is your model, right? So for example, if you find that accuracy of your model is for example 0.6, that would be enough compared to other baselines, and then you can deploy your model. But how we can find out, how we can evaluate the system based on the data that we have. So actually we can split our label data in training and test set, training set and test set. And we get the label data and train and mostly randomly split the data to train and test. And using the training data, we can train the model. And after that, we have our model and we want to evaluate the performance of the system. So we get the test data and then predict labels or values for each data point that we have in the test data, and compare these predicted labels with real data, real labels, and then evaluate that the system is doing a good job in the task or not. So you just need to keep in mind that we need to split the label data in the non-overlapped two sets, training set and test set, and using training data and to training the model, and then test data by the test and test the model based on the test data. So as I mentioned, the splitting of the training and test from label data can be performed randomly, and The test data can be from the label data, or you can get the test data from a time period that come after the training set. For example, you have a system and you are getting some information from the user, and based on this data that we have, from previous user, we can train the model and test on the new user, or for example, new data that we are getting from the system. And a question that we can ask here, that why cannot we just evaluate on the training set? Why we need to evaluate the system on test set? So the reason is that consider that you have a model that is doing a perfect job on the training data set, right? So in this case, you cannot guarantee that your system is going to be a good system on new user or new data, right? Because we already see the training data in the training uh, phase, and the model can remember and or memorize this data, and cannot this cannot be actually a good way to evaluate the model. So if you are evaluating your data, you need to if you are evaluating your system, you need to have a separated data that we didn't see this data in the training process. This is also kind of similar to training, for example, uh, an agent or something like this. So if the agent already saw the exam or something like this, that's not that cannot be a good way to evaluate the agent, because the agent already see the exam or the question that we want to ask from the agent. So after training and training the model, we want to evaluate the system based on some test data, right? So let's use this y hat as a predictive label by the model on an input, an input, and so accuracy is a popular measure in the machine learning that we can use to evaluate the model. And then the definition of the accuracy is finding the for example, we have a test set, and the test set has an n numbers n data points, right? So for each data point, we compare the predicted label by the real label, and this is an indicator function which is one when the input is true, and then is zero when the input is false. So if the predicted label is equal to the real label, the indicator function return one. And in this case, for example, you have 100 test data, and then for half of them, the model is predicting exactly the same labels that we want, which is equal to the true label. So in this case, the accuracy is 0.5. And also this is this can be useful for the classification, but for the regression models, one I just mentioned that in the previous slide I mentioned that in the regression model we are going to predict a real value for each data point. So in this case, for example, we want to predict the price of a stock, and if the price is equal to 2.6, so in this case we don't have any label to use in this indicator function, right? So we need another evaluation for the regression model, which is the mean square error. And mean square error also is similar to the accuracy. For example, we have for each data point, we get the difference between the predicted label and the true labels, and then get the square of that. And actually, the mean square error is the difference between the predicted label and true labels, power of 2. And this is because we want to have a positive value for the mean square error. And because we don't know which one of them is larger value, has a larger value. So we just need to get a positive value for the mean square. So that was the content for the machine learning. And now I want to talk about k-nearest neighbors. And you have some problems in the assignment 5 about k-nearest neighbors. And the k-nearest neighbors is a non-parametric and supervised model in machine learning. And this algorithm can be used for the classification and regression, which means that it can predict labels or real value for each data point in this algorithm. And the basic idea is we need to have similar data points to have similar output. This is the main idea of this algorithm. And I have a definition for the algorithm here, but I will show some example to make it clear. And after showing this example, I think that would be more clear to you what is the k-nearest neighbor. So let's see just a definition for this algorithm. So consider that we get the input, which is x test, and then in this algorithm we want to find the k points. Sorry. So we need to find k points that are actually from the data point in the training that we have. And we have just one constraint here, that these k points should be closest to the input x test. So also, if we consider that we are predicting a y hat here as a predicted label for the x test, we can compute that by a probability distribution over all labels that we have given the x over the all data point that we have over the x, which is the xi, which are co-data point that we have in the area of the x test. So this definition can be, I'm thinking about that. Maybe it's better to see an example before seeing the definition of the algorithm. So, for example, here we have some data point in the training set, right? So the task is classification, and for example, the blue data point are from one class, and then we have a star as a red class, right? And we get a new data point, which is x test, and we want to predict the label for this data point, right? We want to know that this data point is a star or class. And consider also that the k is equal to 3. So in this case, we have two classes, which is star and plus, and we want to predict a label for the new data point. So, for example, here, the x test is the new data point that we get, and then we get k as equal, for example, 3, and we want to find 3 data points that are closest to the new data. So in the next step, we want to predict the label for the new data, which is based on probability distribution over all the labels that we have, and predict the x hat test. So the question is that why we think that the k-nearest neighbor is non-parametric. So the reason is that for each data point, we find a different set of data points as neighbors, right? So this means that the model actually doesn't have any parameter, and then we just need to find some data based on we are deciding about x test based on some data that we already have. We don't have any parameter for that. And how we can decide about the distance between data points, because as I mentioned here, we need to find k points that are closest to x test, which means that we need to find the distance between data points. So we can use Euclidean distance to find the distance between two data points. And actually, the formula of this approach is like this, which is, for example, for each data point, we have actually each data point is a d-dimensional array. In each dimension, we have a feature, right? For example, for each data point, we have 10 features. So for each dimension, we need to get a difference between the values that we have for each features, and then use this formula to find the distance between two data points. Two data points. Actually, this is the simplest way to find the distance between two data points, but uh, actually you can use other approach to find the distance between data points. And as I mentioned, k-nearest neighbors, it can be applied for the classification and regression, right? So for the classification, how we can decide that how we can predict the labels for the new data point. So we can do that by counting the number of labels of each type that are in k data point that are closest to x test, which means that at the first we find k nearest neighbors of the new data point and count the number of labels for these data points that we just find, and then decide about the labels for the new data point. So as another way, also we are giving the x and we are predicting a probability of one class that we have, and we can do that by counting the data point that have exactly same class in k nearest neighbors of this new data point that we want to predict the label for that, right? So I want to show, I show some example of that, and I'm sure that that would be more clear after seeing an example of this. And for the regression task, actually the predicted label can be but can be computed by averaging the actually the labels of the k nearest neighbors of the new data point. For example, if you have three nearest neighbors and each data has a label, a real value. So if you want to predict a real value for new data, you just need to get the average over all the data points. So also this also can be exactly the same thing. You just need to get an average over all the labels that we have in the neighbors of these data point. So I showed this before for the classification task, but for example, here we have two class. One is plus, and then another one is star, and these are training data for the classification. So consider that we get the new data point, and we want to know that what is the label of this new data. So if we consider that k is equal to 3, so we need to find the 3 closest training set points to this data point. So if we want to find these 3 data points, this is close, and I think these 3 are closest data point to these new data points. And because 2 of them, the label of 2 of them is a star, then we can predict the labels of this data point to star, right? So actually the algorithm is finding the closest k nearest neighbors of the new data point, and then decide about the predict decide about the label based on the most common class among the 3 or k closest training set points. And for the regression task, actually, we don't have any label for the data points. We have some real values for each data point. And if we get the new data and the k is equal to 3, we get an average of these 3 closest data points in the new data point, which is 1.83. And a question here is that how we can decide about the value of the k in the algorithm. Actually, the k is a hyperparameter in the algorithm. And the two standard ways for selecting k is validation set and cross validation. And I just briefly explain the validation set and cross validation, but I just want to introduce them. I am not going to detail of that, but if you are interested in that, you can absolutely ask the question about this to standard way to selecting k. So and also these two ways are not restricted to these methods. Actually, we can use these two methods to any algorithm in the machine learning that have hyperparameter. And also there are some complicated methods for deciding about the value of the hyperparameter in the machine learning, which, for example, hyperopt library can be used for doing that. So for the validation set, before that we show that we can split label data to training set and test set. But here we can split our data in training and validation and tests, which means that we have another sets, which is the validation set. And then we train the multiple KNN models with different values of K, for example, K1, 2, 3, 4, 5, 6. And then get the performance of the system on validation set. And then use the K that get maximum score or accuracy on validation set. You just need to keep in your mind that we cannot use test set to decide about the hyperparameter. We need to have another test set. We need to have another set, which is the validation set, and use this set to decide about the k values. So this is also describing validation set. So we get some label data and then split them randomly based on randomly in the training and validation data and test data. And for example, here we use the training data, and then as I mentioned here, we need to train multiple KNN models based on different K values, for example, K1, K3, K5. And then we have these models and then get the evaluation over the validation data. And then, for example, for the K3, we get the highest score, highest accuracy on the validation data, and then we can decide that, okay, for this data, the K should be equal to 3. And for the cross validation, actually cross validation is the same as the validation using validations data, but instead of just having one validation data. In the cross validation, we have folds. Actually, we split the training data into, for example, 5 folds, 10 folds, and then use each fold as a validation data like this, and then for another one, we change the validation set, and then finally we get the best average performance over all folds that we have. As a simple example, consider that we are using cross validation on 2 folds, right? So if we want to have 2 folds, we need to split the training data in 2 folds, and then use the fold one as a training, and then fold 2 as a validation, and we have a test set. Then we use this data in this way and find that the k should be equal to 3. In the next step, we change the fold 1 and fold 2, and now we consider the fold 1 as a validation and fold 2 as a training, and here we find that, for example, the k should be equal to 5, and then we get the average of the k, which is for example, 3 plus 5 divided by 2, and we can decide that k should be equal to 4. This is the simple example of the cross validation, but if you have any question about that, just let me know. I would be happy to talk about that. Also, scikit-learn. I just want to briefly introduce the scikit-learn. You already saw that in assignment, I think, but scikit-learn is a module or library in the Python that has many machine learning functions. For example, you can use function for the pre-processing of your data classification regression cluster. And in the assignment 5, we look at the k-nearest neighbor using scikit-learn. And we also have some example of the k-nearest neighbor in the demo session using scikit-learn. So you don't need to implement the k-nearest neighbor from scratch. You just need to use the scikit-learn to get the result of the k-nearest neighbors. So that's the end of this lecture.